Okay, ladies, this is section 4.2, part 2 of the video. Let's see if we can finish it in this video. We'll see. Okay, so definition: an inflection point is a point on a graph of a function where the concavity changes from upward to downward or downward to upward. Okay, and if f of c is an inflection point of f, then c is a partition number for f double prime. All right. And the steps, or it's really one step and then some sub-steps, but for finding your inflection point, you first find all the partition numbers for C, partition number C for F double prime. And then when you find those partition numbers, you ask yourself, does F double prime change at C, meaning from positive to negative or negative to positive? And is C in the domain of F? And if both those answers are yes, then F of C is an inflection point of F, okay? And so as you can see in this example, and again, I took this from the book, in this first example here, we see that C is a partition number. And so since it changes from positive to negative, then we see how that is concave up, and then at C, it goes like concave down. Okay, so that's C. So C is an inflection point there. And then similarly, you see how this is concave down. And then at that point C, it changes to concave up. And then that's concave up. And then concave down. And then that's concave down. And then concave up. Okay, and so these are just examples of where the concavity changes, and so C is an inflection point in these examples. Okay. All right, let's go to the example. So find the inflection point or points of this function. So we need to find F double prime, right? But first, before you do that, you should make a note, because remember, you have to ask yourself, does F double prime change sign at C, and is C in the domain of F? So let's just go ahead and write out the domain for your function. And you should just get used to doing that, because like you saw in the first videos, that came into play when you're talking about critical numbers, right? Is a partition number a critical number? It has to be in that domain. So you might as well go ahead and just practice finding domains and just writing the domain, even if you don't need that information. Okay. The first derivative, you guys got this: 3x squared minus 18x plus 24. The second derivative, 6x minus 18. Find our partition numbers. So set that equal to 0. Factor out a 6. I'm going through this fast because you have this already. You know how to do this. So x is 3. And so that's a partition number. I'll keep it as the factor form of our F double prime. And so use a test number. So to the left, I can plug in 0 if I plug in. Actually, let me. F double prime of x equals, I'll use, because it's a small number, so 6x minus 18. We plug in 0, we're going to get negative. We plug in 4, we're going to get a positive value. And so since the domain is all reals and it goes from negative to positive, it changes sign, then this is an inflection point. All right, but to be an inflection point, it needs to be an actual point, right? So that means you need to plug in 3 into F to get your answer, to get the actual point. And when you do that, and double check my math to make sure it's correct, don't just write out what I'm writing, you should receive 8. So the inflection point would be 3, 8. Okay, that should be straightforward. Okay, now let's look at example 4. So find the inflection points or points of f of x equals x squared minus 2x plus 5. The first thing we need to do is find the domain of our function. And this one isn't as straightforward. Okay, so x squared minus 2x plus 5. We want to know when that's greater than 0. Now, remember, for any nonlinear inequality, you have to do a sign chart to solve for it. But something else you can do for quadratic is if it's a quadratic inequality, is completing the square. And I know you're like, oh my goodness. And I think, did we do it in this class? I don't know if we did it in this class, but I feel like we did maybe at the beginning of the class. I reviewed it. Okay, so let's quickly review this. So we put our 2x terms together and move the plus 5 to the side. You take half of that number and square it. So negative 2, either times 1/2 or divided by 2, is going to be negative 1. Negative 1 squared is positive 1. So we get x squared minus 2x plus 1. And because we have to balance the equation, and we don't want to change, so our goal is not to change this expression, is to make it look different. And so since we added a 1, we have to subtract a 1, because then that will go off to 0 and we'll even each other out. So we get x squared minus 2x, and then that's going to be plus 4. Oh, actually, no, I'm doing this all wrong. Okay, so from this step here, I just want to show you that that'll be 0. Then you complete the square there, which that's the purpose of the method. X minus 1 squared plus 4. Okay. And again, we're trying to figure out where x minus 1 squared plus 4 is greater than 0. Well, because it's in this form, if you notice, this is squared, right? So that'll always be positive, and that's a positive 4. So that means it's everywhere. It's always positive. So it's always positive everywhere. And so thus, the domain of f is all reals. All right, so I gave you this. Now, you also could have done a sign chart. So just remember, you also could have done a sign chart and taken x squared minus 2x plus 5, found the zeros, did it on sign chart, and test the numbers. The reason why I wanted to show you the other method is because if you look here, that doesn't factor nicely. So you would have to do quadratic formula to find your zeros for this to do the sign chart. And so that would take a little extra work. So you should try, so if this was a quadratic that you could factor, I would say, okay, just use a sign chart. But if it's not easily factorable, then completing the square, you can kind of look to see. That'll help you to determine where the values will be positive, okay? And you may have something like this on your homework, so I wanted to show you that. All right, so let's continue. So that's just sort of the preliminary. We still have to figure out the second derivative of our function, right? So again, we rewrite is ln of x squared. So as you may know by now, especially with practice, that it's chain rule, right? So the derivative of this is going to be 1 over x squared minus 2x plus 5 times the derivative of that, which is 2x minus 2, okay? So this becomes 2x minus 2 over x squared minus 2x plus 5, okay? Now we have to take the derivative of that, and that's going to be what? Yes, quotient rule, you got it. So let's make it a different color since I'm doing the second derivative. All right, the derivative of the top, so that's 2 times the bottom, x squared minus 2x plus 5, minus the derivative of the bottom, which is 2x minus 2 times 2x minus 2. Oh, wow, that's interesting. 2x minus 2. All over x squared minus 2x plus 5 squared. Please do not do illegal algebra that I've been seeing and say, oh, that cancels off. No, 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 no. Only if it's factored in the top and factored in the bottom can you simplify and remove those, what I like to call unnecessary ones. Factor means multiply. So it has to be, everything in the top needs to be multiplied. Everything in the bottom needs to be multiplied before you can, what you all call cancel off. Okay. All right, so all we can do now, let's simplify this numerator. 2x squared minus 4x plus 10 minus, that's going to be 4x squared minus, or plus 8x minus 4. That is not right. let me slow down. I'm trying to do 2 steps in one and it's not working. So that's going to be minus 4x squared. What's that? Minus 4x plus 4, right? Yeah, I was trying to distribute and do all that at once and it just did not work out for me. All right, so that's 2x squared minus 4x plus 10, minus 4x squared plus 8x minus 4, all over x squared minus 2x plus 5 squared, and this becomes negative 2x squared plus 4x plus 6, and double check my work because I could make errors in here, so make sure you double check. All right, so now we need to, so that's f double prime. We need to do a sign chart for that, and so I'm going to have to do another page. So actually, I'm probably going to have to do that on another page, but we need to find, well, what? So the partition numbers are your bad points or where your function is discontinuous, and your zeros, okay? So our zeros is just going to be where the numerator, for a rational function, your zeros is where your numerator equals 0. Okay, and your bad points is where that will equal 0. Well, look at that. It's squared, right? So will that ever be 0? Well, it could be if this inside would be 0. But remember, this was from completing the square. So this is the same as this, which we said will always be positive, okay? So if we did not complete the square, we would have to check to see where that inside could be 0, but we know it'll never be 0. So we won't have any discontinuous points for this function. We'll just have zeros. So let's see if we factor out, I'm going to factor out a negative 2, and we'll have x squared minus 2x minus 3 equals 0. And that's x minus 3. X plus 1 equals 0, so x equals 3 and negative 1. All right, so that's what's going to go on our sign chart for this function. Okay, so I'm going to move to a different slide to put this on. All right, so we found out our zeros was negative 1 and 3, and we put up a z to recognize or signify that there are zeros. Okay, and now I want you to pause and test the point in each of these. So here you can test negative 2, you can test 0 here, and you can test 4 there. Okay, so pause and test your values to see what we're going to have. All right, welcome back. You should have had negative, positive, negative. If you didn't, and you're sure you're correct, I could, always double check my work. So that means we're concave down from negative infinity to negative 1. We're concave up from negative 1 to 3, and we are concave down from 3 to infinity. Okay, and because we switched from negative to positive, negative, these are both inflection points, so I'm going to use IP to represent inflection points, and that was the purpose, right? We needed to find out our inflection points for this problem, and so f of negative 1 and f of 3. So I want you to solve this. I'm not even going to complete this, but I want you to complete it and plug in those numbers. And I'm going to ask you all in class, when we come back to class, when I return back to class, I'm going to ask you all for that information. So just make sure you complete that. All right, and so although it didn't ask for the graph of the function, I did want to show you all, and I know it's kind of small, so just wanted to show you that what's going on. And so if you look to see here, that's from like negative infinity to like negative 1, and then there's a change in concavity, so it's an inflection point somewhere. I'm sorry, it's hard to see, so feel free to do like a decimal somewhere around there. We have an inflection point, and then it starts going concave up until about 3. And then it is concave down there. Okay, so I wanted to, I guess I should have picked a different color for all of them. All right, I just wanted to show you graphically how that would look, although it didn't ask for the graph, but that's where our inflection points, so around -1 and 3, we have an inflection point. Okay, so now let's take it a little step further, and we're going to talk about really analyzing graphs to make sure we understand what's really going on and the additional information we're given with concavity and local max and mins and things of that nature. So look here at this function. This is the function of f prime. And so it says use the graph of f prime to discuss and sketch a possible graph of f. Well, let's talk about this for a minute, right? So I'm going to make a sign chart for f prime. And it looks like, so our zeros, right, or our, let's say, our partition numbers or our critical numbers would be what? What do you think? Looks like here -1, 1, and 2, right? So -1, 1, and 2. Now, we have to be careful because we're actually working backwards in the sense we're given f prime to tell us information about f, the function f. Now, if you recall, the sign chart of f prime tells us where f is increasing or decreasing, right? And so f prime here is from -infinity to -1. We're above the x-axis, right? So that's what the plus and minuses represent for this f prime, right? Where we're above, that's where we're getting that information from. So from -infinity to -1, we're above the x-axis, right? So that means we're positive, and that means the function of f should be increasing from -infinity to -1. Now from -1 to 1, we're still above, right? So that's a plus. So that means we're still increasing from -1 to 1. For 1 to 2, we are above, right? Yes, we are above. And then from 2 to infinity, we're below. So we're still increasing and then we're decreasing. Okay. Now, I guess I'll do another color. So what about, although we're not given information about f double prime, we can glean that because we have the function of f prime. So this, if we look at the tangent lines of f prime, that'll give us the slope of f prime. The slope of the tangent lines of f prime is f double prime, right? That's the derivative. So that tells us this: at -1 and 1, we have horizontal tangent lines, which means f double prime is 0. So -1 and 1. And this takes, let me say, this takes a minute to digest. So you may have to go, and I guess a good thing of me not being in class is that you can look at this video over and over again to make sure you understand what's going on. But again, remember, this is where f double prime is 0, because this is the graph of f prime, not f, okay? And so in terms of, well, now we need to know how to fill out this, right, for f double prime. Well, here is what we have to do. If we're thinking about slopes, from -infinity to -1, we're decreasing. This graph is decreasing, right? The slopes looks like they would be decreasing. If I took slopes of those, if I took any points along this curve, the slopes are decreasing, right? So that means it's negative. Okay. And from -1, all right, so I hope that made sense. From -1 to 1, we're increasing. So it's going to be positive. And then from 1 to infinity, we're decreasing. So it's negative. So that tells us for the graph of f that we are concave down, concave up, and concave down. Now, in order to sketch a graph, and here's where it gets a little tricky, and I think I'm going to, I'm going to stop here. I'm going to finish this problem up, but I'm going to stop here in the videos because I want to give you a chance to finish reading section 4.2 on your own. And then when I come back, we're going to go over this, okay? So here is where we need to put these two graphs together. And this is what we're going to do. I look at from my f prime and my f double prime, I look at the one that has the more partitions, the more intervals, which would be this top one here. And so what I'm going to do is break this interval up. So negative infinity, that's to -1, and then that's -1 to 1, and then that's 1 to 2, and then that's 2 to infinity, right? Okay. Well, I need to sort of bring these two together in order to have a sketch for a possible graph of my function. This is how I'm going to do it. From negative infinity to -1, looking at this first sign chart, I'm increasing. And in terms of concavity, I'm concave down. Okay. All right. From -1 to 1, I am increasing. And looking on here, from -1 to 1, I'm concave up. Okay. Stay with me here. From -1 to 2, I'm increasing. And although here there's not sort of a break between, from 1 to 2, there's not a break here. There's not a 2 on there, right? There's no 2 on there. But from 1 to infinity, I'm always concave down. So I'm concave down. And then for this last one, from 2 to infinity, I'm decreasing and concave down. Okay. And if we look at a general sketch of how, keeping in mind, that's my concave up and that's my concave down. And those are, try to make the curves as smooth as possible. Then I can sort of sketch for each of these sections how it's going to look, right? And then for my graph, though, I need to put it together. So for increasing and concave down, I'm looking over here and I'm looking at which one is increasing. That's that one, right? So this shape is going to look like that. And then increasing and concave up, I'm here. It's going to look like that. Increasing and concave down, again, it's looking like that. And decreasing and concave down is looking like that. Okay. So if we were to put these together, and I don't want to make a new page, I want to keep it here so you can see. So my graph isn't going to be too big, but I think you'll get the gist of what I'm doing, hopefully. And that's why I'm stopping on this problem, so you can really digest all of this. All right, so it's going to look like I am, let's see. Oh, inflection points. I'm sorry, I forgot to mention inflection points. I'm looking at my notes. Remember, the inflection points goes with the f double prime. And so -1 will be an inflection point and 1 will be an inflection point. So that's where I'm turning concavities, right? So just keep that in mind, my inflection points. So the graph is going to look like from negative infinity to -1, I'm increasing the concave down. So I can do something like this, making sure, let's say I go through the inflection point there, and then I'm actually going to make a different. From -1 to 1, I'm increasing the concave up. So I can do something like this. I'm going to put it together in a minute. And let's say my inflection point is there. And then from 1 to 2, I'm increasing and concave down. So it could look something like this until I get to 2. And then at 2, I am decreasing and concave down. So I can do something like this. So this graph, and again, this isn't unique, but as long as you make sure you have your inflection points and your concavities correct, that is a possible sketch for F. So I am over my 20 minutes. I'm stopping here, but definitely make sure you go over and decompact this problem right here. This is the end of the video notes. I'm going to be back, but I want you to finish reading this section on your own, and I'm going to ask you questions from it. So finish reading this section on your own, and then we're going to come back to class to finish this up.